you were given a problem where you were given the capacitive reactance, inductive reactance, and resistance, and asked to sketch a phasor diagram. And it took pretty much the entire hour to do this. And I pointed out that you didn't clearly, most people confirm this, didn't do much with the circular model in their trig or analysis or pre-calculus course. That's criminal, but we can't blame you for it. So we had to take a lot longer to do something that we should have been able to do in a short time. And you're going to need to make that up. In other words, having seen it, having worked through it, you will need to work through a series of problems that we were going to work through in class today. We did work through one of them. So this would be the 170426, I believe, date. We started just with the idea that, okay, you can do a phasor diagram of voltage, resistor voltage. If you have a current with a certain angular frequency and a certain phase angle, then the voltage is going to just be that times the resistance. Now, without going into the phasor diagram for the rest of these, I want to give a quick explanation of this. And let me also point out that you did see this, and I told you it was important to understand this model when we did simple harmonic motion because of what was coming. Well, you know, I understand, end of the semester, you're in survival mode. If you didn't do this, then this is what was coming. And you're not equipped to understand this very well, but you can still do it, and you need to. This is absolutely essential for most engineering fields. You'll see why. The the reference circle model of trigonometric functions. Okay, that's what we're talking about here. If our VR is here on the reference circle, now the vector VR is the vector that travels around the reference circle, follows the reference point around the reference circle. If you project that vector back to the x-axis, we're going to choose to project on the x-axis. We're going to be using the cosine of the angle as measured from the positive x-axis counterclockwise. And again, not to nag you, just to tell you and to alert you to the fact that in the next couple of years, you're going to have to master things when it's time to master them. Otherwise, you'll end up in a downward spiral, or you'll tend to end up in a downward spiral. You're smart people, you're going to do okay, but you're going to do much better if you do things, review your class notes, etc., as we talked in class. So I'm not going to spend a lot of time on that. But this is again kind of a review of what we mean by the reference circle model. So we measure our angle, dot phi theta, and where theta is omega t plus some initial angle that we might call phi naught. And if this is theta for a given t, then this displacement here, which is positive in this case, is going to be the maximum voltage times the cosine of theta. Now we'll say more about that, but let's just see what happens as theta changes. So if theta is right here, then the cosine of theta is here. I'm going to draw a graph. It's going to be kind of small because I don't want to take up much of the room I've already filled on the board. But okay, the cosine of theta could be represented by this arrow here. Now, if we're going to do t versus v, and this is now V. It's not the vector V sub r. That vector's out here in two-dimensional space. It's the projection of this vector onto the x-axis. That's your V. So the V here might be represented by this point. Now the scale of my V-axis here and the scale here are different because this is a smaller picture. But if I represent this little arrow V here, scaling it down for the picture, this would be our arrow that I've labeled V, and this would be the actual voltage. Okay, now the question is, what if we move a little way forward on the reference circle, forward being the counterclockwise direction? So what if we move to this point? Okay, class is going to begin in about 20 minutes. I've got the door open, the hall's going to get noisy. I'm going to step away for just 10 seconds while you figure out what the value of V on this axis would be for this point. Well, it should be clear. We project up here, and now we've got a point here, and we could draw an arrow from here to here. We're just going to get a little bit cluttered. But you see that V has increased significantly. Now I kind of made this just a little higher than I should have, given the scale. Okay, so our V would now be here on the vertical axis. Now this is horizontal, this is vertical. Well, this is the way we graph things, this is the way we picture it on the reference circle. Get used to that, it's no big deal. If we now let the reference vector go to this point, then, well, it is its own projection, and V is a little higher. Okay, so V would be here. Now we go a little further. Say we go here and here and here. What happens? Well, V gets shorter and decreases to 0. So our V, starting here, starts at this, gets bigger, and then decreases back to 0. And then as we go around the circle here, we get a V here, we get a V here, we get a V here, and then here, and here, and here. So we get a V here, and we get a V here. What's happening? We go to the negatives, and V jumps from here to here, and then to here, and then to here. And then it comes back to here, and back to here. Now you might think I'm doing these all at 30-degree angles, but clearly the angles aren't all the same. If you do this at 30-degree angles, of course, then the point you have down here will be symmetric with the point you have up here, and you'll project to the same point. But what you need to see now as we go around the circle, our values of V increase until we get to this point. So we go from here to here. As we go from here to here, then our values of V decrease to 0. Then our values of V decrease, okay, to the negative maximum value, equal to the negative of whatever the radius of the circle represents, and then increase back to 0. Now as they do that, well, let's see, T goes on, right? So let's say our T increments corresponding to these increments look like this. Okay, so in our first T increment, our V value goes from here to here. So we would have a point up here, our first point would be here, and our next point would be up here at the maximum. Okay, that would be this point, and this point. And then we move here, here, and here. Well, that means we're going to come down to maybe here, and then maybe here, and then here. So we're going to have a curve that looks like this. That's from here to here. As we go from here to here, well, we go into negative V values, and we go to some maximum magnitude of that negative V value that's equal to the positive magnitude we had here. So we can draw a line here, and we can draw a line down here. equidistant below the axis, equidistant from the axis with this line, but on the other side. And in 1, 2, 3 more increments, we'll have to be down here. And then what? In 3 more increments, we're going to be back up here. I didn't draw enough of the curve, but it's going to look something like this, and it's going to come back. By the time we've done 12 of these little increments, we're back to the same value of V that we started with. Now that's what the diagram is telling us. So we have to understand this. And I do recommend that you draw a bunch of these. Start at different points, see how the graph works out. Use some bigger circles, some smaller, see if you get bigger swing in your values here, smaller swing in your values, and really get familiar with this model. Now we use this model, again, with simple harmonic motion. You might go back and review that as well.